Hello, good morning to everyone. Myself Keshwasa. I'm from Mechanical Department. A concept on element stiffness matrix for two nodes. Introduction to element stiffness matrix for two nodes. The element stiffness matrix for two nodes is a fundamental concept in structural analysis. It represents the relation between the applied forces and the displacement as the nodes of an element. Understanding the element stiffness matrix is essential for analyzing the behavior of structural under a load. 2.5 into a matrix form fy1 m1 f2y m2 equals to ei by l cube matrix 12 6l minus 12 6l 6l 4l square minus 6l 2l square minus 12 minus 6l 12 minus 6l 6l 2l square minus 6l 4l square and v1 phi 1 v2 phi 2. Here we can observe the two nodes and k equals to ei by l cube y1 m1 y2y m2 y1 m1 2y m2. What is an element stiffness matrix? The element stiffness matrix What is an element stiffness matrix? The element stiffness matrix is an scaled matrix that relates the node displacement to the applied nodal forces. It is a key component in a finite element method for solving the structural analysis problems. The stiffness matrix characterizes the stiffness properties of an element, and it is crucial for calculating the displacement and stresses. Components of element stiffness matrix: equilibrium point for a node I, equilibrium point from node J, displacements of a node I, displacement of a node J xy, and here you can observe the spring with point forces Fi Fj and stiffness from the down. Stiffness matrix, displacement vectors, force vectors. Stiffness matrix we can observe k minus k minus k k. Displacement vectors xi xj, force vectors fi fj. In this the component of element stiffness matrix, the element stiffness matrix consists of spring constants that represent the stiffness of an element in different directions. It is symmetric and pass to different reflecting the physical properties of a structure. The stiffness matrix is typically derived based on the material properties and geometry of the element. Fk equals to F. Deriving the element stiffness matrix. The element stiffness matrix is derived by applying the forces of equilibrium and computables. It involves the formulating the stiffness equations based on the element geometry, material properties, and boundary conditions. The stiffness matrix is often obtained through the uses of analytic or numerical methods. Example of 2 into 2 element stiffness matrix. For a two-node element, the stiffness matrix is a 2 into 2 matrix representing the stiffness of x and y directions. The diagonal elements of a matrix correspond to the axis stiffness in each direction. The off-diagonal elements represent the shear stiffness between the nodes. Notations in the element stiffness matrix. The stiffness matrix is often denoted as a K with subscript indicating the nodes and directions. For a two-node element, the stiffness matrix can be expressed as K that equals to K xx, K xy, K yx, and KYY. The subscript X and Y refers to the direction of stiffness associated with the element. Parallel elements E minus H E into H power 3 by 12 into L minus mu square into A into B. Physical interruptions of element stiffness matrix. The element stiffness matrix represents the resistance of an element due to deformation in different directions. The value in a stiffness matrix qualify how the displacement at one node affect the force at another node. Understanding the stiffness matrix helps in predicting the behavior of structures under the varying loads. Limited work on a stiffness matrix in a literature. Diagonal matrix approximation typically used. Elastic deformation of arrays caused non-diagonal terms kxx, kxy, kxz, kyy, kyz. We can couple between the axial and radial displacements, couple between the axial and rotational displacements, coupling between the radial and rotational displacement matrices. The coupling between the radial and rotational displacement kx theta x, kx theta y, ky theta x, ky theta y, and coupling between the axial and rotational displacements kz theta y, and coupling between the axial and radial displacements kxz and kyz. The element stiffness matrix represents the resistance of an element to deform in a material different directions. The value of stiffness matrix qualify how the displacement at a one node affects the force at another node. Understanding the stiffness matrix helps in predicting the behavior of structures under varying loads. Significance of an element stiffness matrix in structural analysis. The element stiffness matrix is crucial for solving the complex structural analysis problems efficiently. It allows engineers to model the behavior of structures with high accuracy and reliability. By incorporating the stiffness matrix into finite element models, engineers can simultaneously real-world conditions and optimization designs. Transforming the element stiffness matrix. The element stiffness matrix can be transformed to different coordinating systems using the transformation matrix. Coordinate transformations are essential for analyzing the structure with inclined element or non-orthogonal directions. By applying the properties transformations, engineers can simplify the analysis and obtain the accurate results. Applications of element stiffness matrix in beam elements. Beam element stiffness matrix K 12 L cube 12 by L cube 6 by L square minus 12 by L cube 6 by L square 6 by L square 4 by L minus 6 by L square 2 by L minus 12 by L cube minus 6 by L square 12 by L cube minus 6 by L square 6 by L square 2 by L minus 6 by L square 4 by L. Stiffness matrix, displacement vector, force vectors. In a beam element, the stiffness matrix represents the bending and shear stress of elements. The stiffness matrix is crucial for analyzing the diffraction and stresses in beam under a various loading conditions. By incorporating beam elements, stiffness matrix engineering can design and optimize beam structures efficiently. Element stiffness matrix in truss elements. In truss elements, the stiffness matrix characterization and the axial stiffness of elements. The stiffness matrix is used to analyze the deformation and internal forces in truss structures. By considering the truss element stiffness matrix, engineering can assess the sustainability and strength by truss system accurately. Importance of element stiffness matrix in structural dynamics. The element stiffness matrix plays a significant role in structural dynamic analysis. It is used to model the stiffness properties and structural subjected to dynamic loads. By incorporating dynamic stiffness matrices, engineering can predict the dynamic response of structures and ensure their safety and reliability. Limitations of element stiffness matrix. The element stiffness matrix assumes the linear behavior and neglects the nonlinear effect in structures. It may not accurately capture the complex behavior of materials under large deformation or nonlinear loadings. Engineering should be action with using stiffness matrix for highly nonlinear or geometrical nonlinear problems. Updating the element stiffness matrix in a finite element analysis. In finite element analysis, the element stiffness matrix is updated in interactive to account for changes in material properties or boundary conditions. By regulating the stiffness matrix during the analysis, engineers can adapt the evaluation structure conditions and optimize the design. Updating the stiffness matrix ensures the analysis result remains accurate and reliability throughout the simulations. Challenges in implementation. Develop accurate efficiency algorithms for computing system stiffness matrix can be challenging. Handling the large scale structures nodes with numeral elements require advanced communications technology. Engineers can need to ensure the accuracy and convention of stiffness matrix in complex structural analysis problems. Future trends to element stiffness matrix. Incorporating machine learning and artificial intelligence techniques can be future improve the accuracy and speed of stiffness matrix components. Integrating of advanced modeling techniques with the stiffness matrix will enable the engineers to track more complex and resulting structural problems. Conclusion. The element stiffness matrix for two nodes is a fundamental component in structural analysis that underpins the finite element method. Understanding the stiffness matrix is essential for accurately predicting the behavior of structures under various loading conditions. By large ranging the stiffness matrix, engineers can design the safety or more reliable structures and optimization of their performance. References. Thank you.